Hello and welcome back to part 6 of our Stereochemistry course. Last day we talked about projections and which projection will be most stable in Newmann projection or which conformation will be most stable in Newmann projection. So I gave you some questions to do in your time. I hope you've done it. So let us do those first and then we'll start one of the most interesting topics in stereochemistry, the interconversion of projections. So let us do one by one. Okay, the first question states that we have a diacid. Now acids we know have an OH group. So it should help in hydrogen bonding. So it should undergo hydrogen bonding. I talked about this the last class. Those who have missed the last class, please go back and see part 5 of the stereochemistry course. Only after you have completed the part 5, then only come to this section because we are continuing. So if you come directly to this section, you will miss what I am talking about right now. So please visit part 5. The link will provide in the description box below. So as he said, the acid has a OH group. So it should help in hydrogen bonding. And when hydrogen bonding is possible, which conformation projection will be more stable? The Gauss conformation. And when hydrogen bonding will not be possible, the anti-conformation will be more stable. So as I said, the COH, two COH groups are there, so hydrogen bonding will be possible. Then what's the difference between at low pH and at high pH? What does it mean at low pH? Low pH means suppose a pH range of 2 to 6. What does a pH range of 2 to 6 signify? A pH range of 2 to 6 signify that the medium is acidic and there is already acid present, so there will be no change in the acid constitution. So then if we show hydrogen bonding between the two COH, between the two C double bond OH, and because of the presence of hydrogen bonding, the most dominant Newmann projection will be the Gauss conformation at low pH. Okay, I hope you have got that right. So what's the difference at high pH? What is high pH? Suppose a pH of 7 to 10 suppose. Now what is this pH? This is a basic pH. The reaction medium alkaline solution suppose. We have two acids. It has high tendency to give out its OH or give out its proton. That is, it will become CO minus. It will become, the two constituents will then become C double bond to minus, and again here also C double bond to minus. In between there will be these two substitutions. Now whenever it becomes a C double bond to O minus, this O minus can't exhibit hydrogen bonding because it loses its hydrogen. So as soon as you get a basic medium, the acid gives up its proton. So as soon as the acid gives up its proton, it does not exhibit hydrogen bonding. Because of its tendency to not exhibit hydrogen bonding, at high pH this molecule exists in the anti-conformation. At low pH this is a Gauss conformation. This is how important this molecule is. So you understood why this differentiation of low pH and high pH is given. So you have to, whenever you get a question, you have to see very carefully. In a question, if the examiner gives you a low pH and high pH, do not think that it is not for any reason. It must have a reason. It must have a definite problem within it. Like here at low pH, the acid exhibits hydrogen bonding. But at low pH, because of it being an alkaline solution, it gives up its proton. As soon as it gives up its proton, it cannot exhibit hydrogen bonding. Because it doesn't exhibit hydrogen bonding, it exists in the anti-conformation. Or the most stable Newmann projection is the anti-conformation. Those who have got two of them correct, trust me, you have learned everything about Newmann projection. You can do anything Newmann projection about it. Okay, let us do the second one. Here we have an acid and a CH3 group. Now CH3 group means a carbon. Carbon is not so much electronegative to undergo hydrogen bonding. So even though there is an acid which is ready to undergo hydrogen bonding, but due to the low electronegativity of carbon, the other part of the molecule cannot exhibit hydrogen bonding. Remember I told you in the last class, both the sides must have groups which can exhibit hydrogen bonding. If one of the sides have a group like methyl or any group which cannot exhibit hydrogen bonding, then it will exist in the anti-conformation. So this molecule exists in the anti-conformation. Let's do the third one. This is very easy. We have a OH and an NH2 group. And both these groups can exhibit hydrogen bonding. OH and NH2, they are highly electronegative. They have hydrogen present in them. They can exhibit hydrogen bonding. So this exists in the Gauss conformation. These are very easy. The fourth one also is very easy. It is similar to the second one. Fluorine can exhibit hydrogen bonding, but methyl carbon is very low electronegative. Due to it being very low electronegative, it cannot exhibit hydrogen bonding. It is like the number 2. We saw one part of the molecule can exhibit hydrogen bonding, but the other part doesn't attach to other part doesn't come to its aid. So this molecule also exists in the anti-conformation. I'm not drawing the structure. I hope you have got it by now, what is anti and what is gauge conformation. So if I tell you gauge, you can understand what is the gauge conformation I'm talking about. You can draw the Newmann projection. So I'm not drawing it here. If you have not understood how to draw the Newmann projections, then do let us know. We'll cover it again so as to make it helpful for all of you. Number 5, we need to draw the Newmann projection. And why I need to draw the Newmann projection? Now if you see from here, it has 2 methyls. None of the groups are there which can exhibit hydrogen bonding. So it has to exist in the anti conformation. The answer is anti. But which anti? And why there is more than one anti? Let us look at it. What are the Newmann projections that are possible? Now see, I am drawing with respect to this bond, or this carbon and this carbon. So one of the carbon has 2 methyl substitutions and one of the carbon has only 1 methyl substitution. Okay, so these are the probable projections that we have. This is a gauge conformation, so this is ruled out straight away. So this does not exist. So this number 2 projection is not the most stable projection. Why you can see? Because there is 2 methyl-methyl interactions. Here there is a methyl-methyl interaction. Here also there is a methyl-methyl interaction, which is very huge, which is much more than a methyl hydrogen interaction. That's why this 2 is ruled out firstly. Now let us see at number 1 and number 3. First of all, can you distinguish between them two? Let us see the interactions. You can distinguish, but let us see the interactions. Whether you can distinguish between the interactions. See here, there is a methyl-methyl interaction and a methyl hydrogen interaction. Or we can say there is one methyl-methyl interaction. Others are all methyl hydrogen. Here also there is one methyl-methyl interaction. One methyl-methyl interactions. Others are all again methyl hydrogen. So both 1 and 3 are the same energy. Why they are the same energy? See, this is anti with respect to this methyl. If I number them, this is 1, suppose this is 2. Again this is 1, this is 2. Again we are keeping the front of the molecule fixed. We are changing the positions of the back carbon atom. So the methyl of the back carbon atom is rotating. The 2 methyls of the front carbon atom are fixed. So this case it is anti to methyl 1, but this case it is anti to methyl 2. But the structure of the molecule is such that in both the cases the interactions and the interaction energy is the same. So both 1 and 3 are correct projections, are correct Newmann projections. So in your exam, if you give both 1 and both 3, or you draw either of them, the examiner is bound to give you correct. I asked you to draw the structure of this one. Obviously this exists in anti, you can understand this, but this molecule exists in either conformation 1 or in conformation 3. I hope you have done it. I hope some of you or most of you have got all of them right, because this is easy and we have gone through this in the last class. So today after learning all these projections, we learn how to interconvert them, and this is one of the most important from exam point of view and also from the point of view of understanding. So today mostly we will talk about tricks. So see the video very carefully, because we will only talk about tricks today. How do you convert one from the other? And don't miss a trick, because if you understand these tricks, there are not much tricks are there, very small tricks are there, but if you understand the tricks, you can convert any projection to any other projection. So don't just miss out any part of the video, and understand and listen to it very carefully. If you know the tricks in one video, like in a 30-minute, 40-minute, you can understand all the tricks, you can do any projection possible. Let us go one by one. We are converting a wedge dash to a Fischer projection. What is a wedge dash? This is a wedge dash. What is a Fischer? We talked about last day. This is a Fischer projection. Any groups are there. I'm just giving a random example. So we have to convert this example to a Fischer projection. How do you convert that? Suppose we keep our eye here. And we are seeing from here. So let us draw, and I told last day that the vertical plane contains molecules which are in the plane, or vertex or centers which are in the plane. The horizontal line in a Fischer projection contains groups which are out of the plane, either above the plane or below the plane. So let us draw a Fischer projection. There are two intersections. This is the intersection, this is the intersection. So let us draw two intersections. You understand what is intersection? This is an intersection. In a Fischer projection, wherever there is a cross, first you have to understand how many intersections are there. This will come in handy in this example. We will come to it later. But let us see this. So there are two intersections. Because why two intersections? Because there are two substitutions. See here, there is an atom which has no substitution. So only groups or only atoms which are substituted constitute an intersection of Fischer projection. If you don't have a substitution in a wedge dash or in any other projection, those do not constitute as intersection in Fischer projection. Suppose here I don't need to draw it separately, like here CH2 and Me. We can directly say it is an ethyl and I can put it in the plane. We'll come to it. So we have two intersections. This is one intersection, this is another intersection. Okay, let us put the methyls first. Here we are putting a methyl, here we are putting a methyl. Suppose I'm naming them. This is number 1, this is number 2. And I'm seeing from here. Remember where I'm seeing it, because this is very important when I tell you the tricks. From wherever you're seeing it, it is very important. The whole molecule changes, or the whole system of view changes if you are seeing it from the right side. I'm seeing it right now from the left side of the molecule. If I'm seeing it from the right side, the whole projection changes. So methyl 1 is at below, methyl 2 is at the top. You understand those. Now we have a methyl at the first carbon, suppose a C2 carbon, a methyl which is above the plane and a hydrogen which is below the plane. How do I represent them in Fischer projection? I have no idea how to represent them in Fischer projection. So I'll tell you some tricks, and do not forget those tricks because this is very important. So I'll draw two tables. First I'll draw WD, which is wedge dash, another is Fischer. Okay, and do not forget this table. If you are making notes, write this table down in your note copy because this is very important, and from here you can solve any wedge dash to Fischer and vice versa. What I say, suppose in wedge dash, if you have a right side above the plane, goes to the left in Fischer projection. I'll write them first, then I'll come to what is this. And left side above the plane goes in the right side of Fischer projection. So what it says, right side above the plane goes to the left in Fischer projection. What is left? Fischer projection is left is this side. On this side it goes. Left side above the plane goes to the right of Fischer projection, means on this side. Let us see. Suppose I put an arrow here and I see through here. Suppose I see an arrow here and I see through here. Suppose I draw the molecule like this. This will make it easier to understand. This is much easier to understand. So you're keeping the eye here. You're keeping your eye here. So I'm seeing from here. I'm seeing through this side. So suppose I see at C2 carbon. So C2 carbon, C, and the left side, all the substituents are on the left side of the C2 carbon. See, this is the left side. So you can see, if I'm seeing to straight, if I'm seeing through the plane, this is the left side, this is the right side. So at the C2 carbon, it is on the left side. All the substituents are on the left side. On the C3 carbon, both the substituents are on the right side. That's what I mean by left side and right side in a wedge dash projection. So what is it? If I'm seeing from here, if I'm seeing through here, now see very carefully, I'm seeing through here. Both this hydrogen and this methyl are on the left side of the plane or left side of the straight line. And both this hydrogen and methyl at the C3 position are on the right side of the straight line. Right side. So what it says that if in a wedge dash projection, if a substituent is on the left side and if it is above the plane, it goes on the right hand side in a Fischer projection. So we have a left side and we have above the plane is a methyl. So methyl goes to the right side in a Fischer projection. Okay, so here methyl goes and here the hydrogen goes. Understood why? See, again we are seeing to this side. See, both this hydrogen and methyl are on the left side, and left side above the plane, that means this methyl, which is the substituent which is above the plane on the left side, which is the methyl, that goes to the right in the Fischer projection. That goes to the right. This is the right. This is the right in the Fischer projection. So that goes to the right in the Fischer projection. Let us get to C3. So now it is on the right side. Both these hydrogen and methyl are on the right side. What it says, right side above the plane. What we have right side above the plane? Hydrogen. Right side above the plane goes to the left side in the Fischer projection. So right side above the plane hydrogen, this hydrogen goes to the left side of Fischer projection, and we write the methyl. This is our Fischer projection of this molecule. So you understood, students? This is how we change a wedge dash to a Fischer projection. Remember this table. you can understand other things, because obviously right side above the plane goes left means below the plane goes to the other side, because there is only above the plane, below the plane. Remember this table. In a wedge dash, right side above the plane goes to the left side in a Fischer projection. If there is a left side above the plane, it goes to the right side in a Fischer projection. This is it. Here you can do everything in a from wedge dash to a Fischer projection. Just remember this table. They can give you any wedge dash, you can convert into Fischer projection simply by following these two rules. You first draw the molecule, put your eye in some side and see through the plane, and then you see which side the substituents are there. If you see right side, the substituent which is above the plane goes to the left in a Fischer projection. If you see substituents on the left hand side, the substituent which is above the plane, the left hand side, goes to the right in a Fischer projection. Got it? So if you have got it, please pause the video here and do this one. Do this number 2 one. I'll show you how to do it. Don't forget this table, students. This table is all you need required to know. You don't require to remember anything else. So you can see any wedge dash projection, you can change it to Fischer projection. You just need to remember these two rules. These two rules are it. That table is enough to convert any wedge dash to a Fischer projection. Let us see here. Suppose again I put my eye here and I see through this side. So first I draw the vertical plane. What is in the vertical plane? Again, how many intersections are there? 1, 2. Again, as I said, only those intersections which have a substitution, those intersections will be drawn in a Fischer projection. See here, this molecule, this carbon has no substitution. So this does not enter into this intersection of Fischer projection. But as soon as it has a substitution, it enters into the intersection. Here there are two substitutions, or two carbons are substituted. So there are two intersections in a Fischer projection, this one and this one. So I'm seeing through here it is a methyl. So methyl is below, methyl goes below. We go through this 1, 2 and 3 position, we have a CH2Me. That is, we have ethyl at the above. This is how we write. Whenever we don't have a substitution, we write the group that is. We don't write it CH2 in hydrogen, then again methyl. We directly write ethyl. Okay, let us see then. Let us apply our rules. We are seeing through this side. So at the C2 position, this carbon is C2. We have substitution on the left hand side. See, we are seeing from the straight line. Substitutions are here. So we have substitution on the left hand side. Left hand side above the plane goes to the right side in Fischer projection. What do we have above the plane? Methyl. This goes to the right side in a Fischer projection, and the hydrogen goes to the other side. Again, this is the right side of a Fischer projection. Don't confuse between the left side and right side. If you just don't confuse and remember the rules, you can convert anything to any wedge dash to any Fischer projection. You will not get ever, you will never do anything wrong. Let us see at C3. This is C3 suppose. C3, the substitutions are on the right hand side. Right hand side above the plane in a wedge dash projection goes to the left side in a Fischer projection. What do we have above the plane? Hydrogen. See, this is above the plane. So this goes to the left hand side of a Fischer projection, and the corresponding methyl occupies the other position. In this way you can convert any wedge dash to any Fischer projection. Remember the rules, remember this table. This table is highly important. Just remember this table. This is a very important trick to convert a wedge dash to a Fischer projection. Wedge dash right side above the plane goes to the left hand side in a Fischer projection. A left side above the plane in a wedge dash goes to the right hand side of a Fischer projection. And don't confuse the left and right. If you don't confuse between them, you can convert any of the wedge dash to any of the Fischer projections. Similar way you can convert any Fischer to any wedge dash as well. Again, just follow the rules. Again, whenever you see left on the Fischer, if you want to draw it on the right side, you draw it above the plane. If you want to draw it on the left side, draw it below the plane. The same. If you have understood this table, you can convert wedge dash to Fischer as well as Fischer to wedge dash. It's absolutely the same. Let us go to the next one. What is the next one? So we want to convert a Sawhorse to a wedge dash and then a wedge dash to a Fischer projection. So it's a continuous process. We know how to convert a wedge dash to a Fischer. This we know, but first we need to convert this to this, and then we will convert that to the Fischer using our knowledge. Again, remember the trick. I'm just telling the tricks here. How do we convert a Sawhorse to a wedge dash? We draw it. Okay, first let me draw this Sawhorse in a form which is much more easier to understand. This is the same, right? Okay, you have to convert this to a wedge dash projection. Okay, how do you convert this to a wedge dash projection? First to the line, this line we just simply draw it. We don't have to do anything else. Then we put the tail of the y. Always remember the tail. Here the tail is towards the upward side. The tail will be towards like this also. The tail will be below as well. Just put the tails in the plane in a wedge dash projection. So I just put the tails in the plane and as it is, don't change the orientation. See, the methyl is on the above side here. I put it on the above side of this line. Again the methyl, the tail is on the above side here. I put it on the above side in a wedge dash projection. Don't change this conformation. If you change this conformation, the whole trick fails. This trick is designed in such a way so as you don't have to change the conformation. Never change the conformation. This is an eclipse conformation. If you have seen the last video, you will know what is an eclipse conformation and what is a staggered conformation. When you need to convert a sawhorse to a wedge dash and then to a Fischer, suppose a sawhorse to wedge dash right now, don't change from an eclipse to staggered. If it is given in eclipse in sawhorse, keep it in eclipse in wedge dash. Don't change it to staggered in wedge dash. Keep it as it is. Then only the tricks follow. So I keep it as it is. How do I draw? First a straight line, which is the same straight line. Then I see the tail of the y and I put it in the plane. See, these are all in the plane. And I draw the substituents as it is. I draw the substituents as it is. Don't forget this. Now the trick comes into play. What does the trick say? That whenever I draw a straight line through this, suppose I draw imaginary straight line through this, okay, through the tail, and I extend it towards the head. Whatever falls on the right hand side, here chlorine, here hydrogen, so whatever falls on the right hand side will go above the plane, So suppose I have like this. I draw first, one is above the plane, one is below the plane, obviously. Whatever falls on the right hand side, so what do? I extend a straight line through the tail through its head. Whatever falls on the right hand side goes above the plane in a wedge dash projection. See, chlorine falls on the right hand side, it goes above the plane in a wedge dash projection. Corresponding, the hydrogen goes below the plane. Again, what falls on the right hand side in this case? The hydrogen falls above the plane. Hydrogen falls on the right hand side. So hydrogen goes above the plane. Corresponding, the fluorine goes below the plane. You have your wedge dash projection. Let us repeat one more time for understanding. Firstly, I draw the straight line. I'll do it again. I draw the straight line as it is. I draw this straight line as it is. I draw the tail as it is. Don't change the tail. If it is eclipsed, if the tail is towards upward side, keep the tail towards the upward side. Don't change it to the downward side. You may say, okay, I keep both these methyls below. Then this trick fails. You have to keep the tails as and how it is. Keep the tail as it is in sawhorse. It's the same way in wedge dash. Don't change the conformation of the tail. If the tail is pointing upwards, keep it upwards. If the tail is coming downwards like a normal Y like this one, keep the substituents downwards and it falls in the plane. I draw this. Then I do what? Then I go to the Sawhorse projection. I draw a straight line from the tail extending through the head, to the middle of the head. Both sides I do it. And then I see whichever substituent is on the right hand side goes above the plane. And the other substituent goes below the plane. Again, whichever substituent is on the right hand side goes above the plane. The other substituent goes below the plane. We have our wedge dash projection. Simple enough. Now we have to convert this into Fischer. You know this by now. So I'll do it very fast. I keep my eye here. Very flexible eye. I see through here. First I draw. How many intersections do we have? 2, right? We have 2 intersections. This is another intersection. This is another intersection. So this is intersection. I am seeing through here. Suppose I put 1, 2. So I'll write the methyl 1. This is 2. Let us apply our trick. So I am seeing here. I am seeing through here. This substituent falls on the right hand side. On the right hand side. Both the chlorine and hydrogen on the right hand side. So right hand side above the plane goes to the left of the Fischer projection. What is right hand side above the plane? Chlorine is the right hand side above the plane. It goes towards the left side of a Fischer projection. Okay, it goes to the left side of a Fischer projection. Again, let us go at this intersection. Again, both the substituents are on the right hand side. Simple right hand side. Again, right hand side above the plane goes to the left hand side in a Fischer projection. What is right hand side above the plane? Hydrogen. It goes to the left hand side in the Fischer projection. The fluorine comes here. This is your Fischer projection. This is your final Fischer projection. So you understood how to convert a Sawhorse to wedge dash and then a wedge dash to Fischer. What comes in exams is, suppose they give you Sawhorse like this. They give you a Sawhorse like this and ask you draw this to a corresponding Fischer projection. How do you do it? You convert it to a wedge dash first and then you know from wedge dash to Fischer. How do you convert it from Sawhorse to wedge dash? This is the trick. Okay, I have not written it, but if you have followed the video, you would have made your own notes. So you convert the Sawhorse to a wedge dash to this trick. Apply the second trick to convert a wedge dash to a Fischer. Simple enough. It's all a trick business. Let us see the second one. This is a staggered projection, by the way. So let us draw it in the way we like it. This methyl is coming down. This methyl is going up. Remember, don't change the conformations. As I said, if the tail is down, keep it down. If the tail is up, keep it up. This is the same, right? Both are the same. I need to convert this Sawhorse projection to a wedge dash projection first and then to a corresponding Fischer projection. Let us apply our knowledge of tricks. Let us see. So we draw the line as in how it is. This methyl goes on the top, this tail is on the top, this tail is at the bottom. So one Y is like this tail is pointing down, another Y is like this, the tail is pointing up. Don't change. See, I didn't change the conformation. Here the methyl is pointing up, I kept it up. Here the tail is pointing down, the methyl is coming down, I put it down. Remember, these are not down, these are in the plane. Just the drawing is in like this. I draw a line through the tail. Same, I draw a line through the tail. This is an imaginary line, okay? This does not exist, by the way. I draw a line through the tail. I see what is on the right hand side. Okay, I find a chlorine. Whatever is on the right hand side, it goes above the plane. So this chlorine goes above the plane. This hydrogen goes below the plane. Simple enough. Once you understood the tricks, this is very easy. This is like a child's play. Again, I draw a straight line. I see what is on the right hand side. Okay, I get a hydrogen. It goes above the plane. Another, and fluorine is there. It goes below the plane. You have your wedge dash projection. This is your wedge dash projection. Very simple. This is how you convert a Sawhorse to wedge dash. Let us see how to convert in a Fischer. You know by now. Let us put an eye here. First, always draw the eye so you understand. You draw good eye, you draw bad eye, doesn't matter. You have to just understand the Fischer projection. Okay, I put an eye here and I see to this side. Okay, how many intersections? 2. Very good. So I draw 2 intersections of Fischer projection. Okay, again I number the methyls. This is 1, this is 2. The methyl 1 is down. Why this methyl 1 is down? Because this is the first one I am seeing. If I am seeing from here, this is the first carbon I come across. Then I go to this carbon. So methyl 1 comes down. This methyl 2 goes up. Okay, what are the tricks? It says it is, we are seeing to here. So this chlorine and hydrogen both are on the left hand side, right? Both are on the left hand side. You understand what is left and right? I am seeing to here. I am seeing to here. Both chlorine and hydrogen on the left hand side. Left hand side above the plane goes to which side in Fischer projection? It is just the opposite. How do you remember it? I forgot to tell you this. How do you remember it? Just it is the opposite. Right hand side above the plane goes to the left hand side. It is just the anti. Right hand side above the plane goes to the left hand side. Left hand side above the plane goes to the right hand side. That's it. Nothing else you need to remember. So left hand side above the plane goes to which side? It goes to the right hand side. So chlorine comes on the right hand side. And we have a hydrogen. What happens with this carbon? See, the substituents are on the right hand side. This both hydrogen and fluorine are on the right hand side of the straight line. On the right hand side of your point of view. Always keep your point of view. Always draw your point of view from the first. That will be easier to understand. Someone may draw your point of view here. Yeah, you are very welcome to draw. Fischer projection changes in that way. I draw it on the left hand side. It becomes easier for me. It's anyway, you are justified to draw your eye on the right hand side. So let us see here. So what happens? These substituents are on the right hand side. Right hand side above the plane goes to the left hand side in a Fischer projection. What is above the plane? A hydrogen. Why it goes to the left hand side? Okay, to the left hand side, and then we have a chlorine. You have your Fischer projection. Final answer. If you have got this correct, mark yourself, you got 1 marks. or how many marks, 2 marks, 3 marks, doesn't matter. So you got a sawhorse, you can convert it to a wedge dash, you got your tricks. Then wedge dash, you can convert into Fischer, you got your tricks. Last one, let us see. You have to convert in Newman, last projection. If you give us a sawhorse, if you give me a sawhorse, I will convert it into Fischer by through wedge dash. If you give me a wedge dash, I can convert it to Fischer through nothing, direct. How do you convert it to a Fischer if you give me a Newman projection? Okay, so I will go through these steps. I will convert Newman to sawhorse first. This is something I don't know right now. I will tell you. Sawhorse to wedge dash, we know the trick. Wedge dash to Fischer, we know the trick. So last two parts we know. We just need to do the first part. Let us do it. I'll give 2 examples. I'll show you 2 examples. Then I'll give you a lot of questions to solve, 5-6 questions to solve. Please, you also solve questions from your book. You can refer any book and do the questions. Try to solve any projection to any other projection. You take up any projection, try to change it to any other projection. Mostly they give you from suppose Newman to Fischer, or sawhorse to Fischer, wedge dash to Fischer. Mostly the end part is Fischer only. But you change it from any to any. If you know these tricks, you can convert any projection to any projection. Any random projection to any random projection. This is the last one. Let us see. How do you convert this Newman to sawhorse? Again, I just draw it as it is. See, these are 2 Y's. One Y is like this, the other Y is like this. That is the one containing methyl, hydrogen, bromine. The other Y is like this, containing methyl, fluorine, chlorine. Okay, suppose I draw it like this. I put the methyl here, one Y like this. Other Y, I draw it. First I draw the Y's. Then I put the substitutions. So what is this Y? This is methyl, hydrogen, bromine. I draw it as it is. Don't have to change anything. Draw it as it is. Methyl, hydrogen, bromine. Again, other case, methyl, fluorine, chlorine. Draw it as it is. You have your Sawhorse projection. This is the easiest. You first draw the straight line, then you draw the 2 Y's as in how it is shaped. Again, don't change the shape. If the Y is, one Y is pointing downwards and another Y is pointing upwards like this, draw the Y's in the Sawhorse projection as and how it is. Don't try to change the side of the projection. Don't try to change a Y pointing downwards to a Y pointing upward. If a Y is pointing downward, keep it downwards. Don't change. This is the simplest way. If you change it, all the things go away. You won't be able to apply any of the tricks. See, this is very simple. You just draw it as and how it is. But don't try to change. Like if I am saying one Y is like this, another Y is like this, don't go to the exam center and draw both the Y's like this and say, okay, I changed one of them because I can rotate. Don't. It changes the whole meaning of the projection and you will always get it wrong when you try to interconvert. Draw it as and how it is given. See, one Y is like this, one Y is like this. I drew it as and how it is given. It's very easy. How do we convert this Sawhorse to wedge dash then? So we understood how to convert a Newman to Sawhorse. Very easy. Then we apply our tricks. First we draw a wedge dash. Then we convert into Fischer. How do I do? I draw the straight line. I draw the tail of the Y's. I draw the tail of the Y's. These are the 2 tails. Then what do? I draw an imaginary straight line from the tail extending to the middle of the head. And I see what is on the right side. What is on the right side? Bromine is on the right side. That goes above the plane. Bromine goes above the plane. What goes below the plane? The hydrogen that is pending. Simple enough. What here? What goes on the right hand side? Chlorine is on the right hand side. So where it goes? Above the plane, right? The other part, fluorine, goes below the plane. This is your wedge dash. Simple. Okay, last part, and this is to convert into Fischer. You have understood by now. Let us put my eye here again. I am seeing through here. I draw the intersections. And I told you last class, this vertical line means in the plane, horizontal line means out of the plane. I am not repeating it here because I told you in the last class. So let us do this. So here we have a methyl. I can number them. 1, 2. Methyl 1 comes downward because this is the first carbon we come across. Methyl 2 goes up, but this is the second carbon we come across. So here the hydrogen and bromine are which side? Come on, tell me which side. This is very important. Understand me, left hand side or right hand side. Which side? Tell me. It's on the right hand side, right? So right hand side above the plane goes to which side in Fischer projection? Left side in Fischer projection. Left side above the plane goes to the right side in Fischer projection. So chlorine goes to the right side, fluorine goes to the left hand side. You got your final Fischer projection. These are the 4 projections you can get. So if anyone gives you any Newman projection, you can convert into Fischer projection. Convert into Sawhorse first, very easy. You don't have to apply any tricks, just keep the molecule as and how it is. Then from Sawhorse to Wedge dash, you have to apply one trick. That's good enough. You get your Wedge dash. Once you get your Wedge dash, you have to convert into Fischer. Just one table, remember. Two points are there in the table. Remember these 2 points, you can convert any Wedge dash to a Fischer projection. Last example for today, and then we will wrap up this projection. So we have to convert this Newman to Sawhorse, and then to Wedge dash, and then to Fischer. Simple enough. If you have got this by now, I think most of you have got this by now. Please pause the video here, do it for yourself, and then see the solution. Okay, let us convert this into Newman first. What did I say? I draw the straight line. Here the 2 y's are like this. First you have to understand the nature of the y's. Whenever you are converting a Newman to a Sawhorse, you have to understand the nature of the y's, which side the tail is pointing. See, 2 y's are like this. Both the tails are pointing upward. This methyl is one of the tail, this chlorine is another tail. Well, you may say, okay, the NH2 may also be the tail. But whatever the drawing is given, in that sense, chlorine is the tail. Yeah, you may rotate this and the NH2 may sometime come here, but you are not changing the projections. Right now, the examiner has given us some projection. We have one Newman projection, and we have to change that to a Fischer projection. That's the question. You may say that, okay, this is a fully eclipsed conformation. I want to change it to a cross conformation and do. Don't do that. If it is in a fully eclipsed, do it in a fully eclipsed. If it is given 90, do it 90. If the question is given in Gauss, do it in Gauss. Just don't change the size of the Y or the shape of the Y. If the Y is pointing upwards in a Newman projection, keep it upwards in a Sawhorse projection. Then you have got the whole molecule right. As soon as you try to change the tail of the Y, the whole molecule goes wrong. And if you see here carefully, if you change from Newman to Sawhorse, and suppose you say, okay, the 2 y's are pointing downward, you keep both the y's upward, and then you change that Sawhorse to Wedge dash and to Fischer. The Fischer comes wrong. So don't change the conformation. I'm telling you many times in this video, I've told you many times in this video, don't change the size of the conformation. From a Newman to Sawhorse, you first understand the nature of the Y, and then draw it in a Sawhorse. So both y's are like this. In this case, I draw it. And I simply put the substituents: methyl, hydrogen bromine, chlorine, fluorine, NH2. I get my Sawhorse. It's very simple. Newman to Sawhorse is very simple. You don't need to apply any tricks. Just see the molecule, change it. It's very simple. Then you have to change it to Wedge dash. I will do it very fast now because I have already explained it a lot of times. So methyl chlorine, I draw a straight line, an imaginary line. This is imaginary. This doesn't exist, by the way. What is on the right hand side? Bromine. So bromine goes above the plane. The hydrogen comes below the plane. What is on the right hand side? NH2. NH2 goes above the plane. Fluorine goes below the plane. Again, I have to convert into Fischer. How many intersections are there? 2 intersections are there. Good. One, I keeping my eye here, so you always draw your eye. Don't forget to draw your eye. So you have to understand where you are seeing it from. I am seeing it from the left hand side, you may see it from the right hand side. The whole projection of the whole conformation of the Fischer projection changes. So this methyl comes first, this methyl goes below, this chlorine goes up. Which side is substitution? It is on the right hand side. Right hand side above the plane goes to the left in Fischer projection. What is above the plane? Bromine. Bromine goes to the left. Which side is this fluorine NH2? It is again on the right hand side. So I am seeing through here. See, this fluorine NH2 comes on the right hand side. You understood what is right and left? If you understood what is right and left, it is very easy. You are seeing through here. This falls on the right. This falls on the left. If you are seeing through here in a Wedge dash projection, whatever comes on this side falls on the right. Whatever comes on this side falls on the left. This you need to understand. You keep your eye here. You see it. You are seeing from here. This side right, this side left. Right side above the plane in a Wedge dash projection goes to the left hand side in a Fischer projection. Left side above the plane in a Wedge dash projection goes to the right hand side in a Fischer projection. You understood by now. So this is on the right hand side, this fluorine NH2. What is above the plane? NH2. It goes which side? It goes to the left hand side, and the fluorine comes here. This is your Fischer projection. Got it? I hope every one of you understood this. I hope I've tried to make it as fun for you as possible, because this is very easy. You just have to use the tricks, nothing else. Like stereochemistry is made up of visualization, but in this case you just have to understand the tricks. These are 5 examples. I think I have done this one, so don't do this one. Rest 4 you do and let me know. So we'll come in the next video and we will solve this first. And I request you all to take up any book of any IITJEE examination or any question paper and try to solve this projection changing. There will be lots of questions you will find where they will give you a Newmann projection and ask you to change in some other projection. So do it, try to change. If you know the tricks and you know the rules by now, mostly tricks, if you know the tricks by now, you will know how to change any of the projection to any other projection. I have given all of this in Newmann, Sawhorse and any other projection. Just change them in Fischer projection. These are very easy. So do solve them and come to our next video. Next video will start with enantiomers and diastereomers. We are mostly done the stereochemistry course. Like we'll take 2 or maximum 3 more videos to complete the stereochemistry course. So next day we'll start with enantiomers, diastereomers. And I hope you have liked this class. I hope you have understood how to convert projections from one to another. And I hope you enjoyed this class by mostly. So if you have enjoyed, please do like, share and subscribe, because we need you to subscribe, because if you don't subscribe and if you don't press the bell icon, you miss out, we miss out. So please do subscribe and please look out for our videos and look out for our channel IITJEE Chemistry Tutor. Do subscribe and we'll meet you in the next class in enantiomers and diastereomers. Till then, goodbye and thank you.